Ah, making a video. Sorry. It happens. Anyway, so I thought I would do a response video to this Wallace Thornhill, Long Path to Understanding Gravity. So he's one of these electric universe kind of people. There's this Thunderbolts project. Somehow is connected to this idea. Kind of Teslian, I guess, or something. I'm just trying to provoke conversation with even some of those people. The only person commenting on my videos is the real crazy ones. I guess he deleted his comment. I don't know. He's made some sort of, whatever his name is, the Truth Quest or whatever, and he's got that whole religious Bible thing, the rewritten Bible that has physics in it. Everything's just a tornado, you see. It's all this. But there's a lot of people doing that. You know, a lot of people doing this. Everything's tornadoing. You know, there's vortices. And, it's a little different. Yeah. It sort of looks like that, even in Einstein's gravity. You just throw something in there and it spins down. But that's just a consequence of the reality, not a part of. It's not the mechanism. It's, even galaxies, I guess, they kind of do that a little bit. But yeah, like I said, it's a consequence. It's not the function. So these people have these. So I played the first 16 minutes or 17 minutes, whatever. And he doesn't say much. He's a good speaker, and pointing out how physics doesn't really give answers to questions. It just sits there and gives you a mathematical equation, which is just a relationship. So let's understand, like E equals mc squared. It's just pointing out a relationship that mass is pretty much full of energy, and that energy can be in the form of mass. It can be stored there. It's like a battery. But it's just forming a relationship, and there's just relationships as part of the equation. So when you expand a relationship, say, the gravitational constant times the mass divided by the density squared, no, radius squared, it's got to be something like that. R squared, even though it says D squared there. That's by my vision. Anyway, I guess distance, that is, D, I don't know. Anyway, it's just, these are just partly acknowledging things have to add up, or there's components to everything's function, and you're just saying, by creating these symbols and these letters, you're just saying these are symbols and letters for different kinds of things that things have. We have acceleration, we have velocity. We have these things. There's components of us that are accelerating. There's components of us that have velocity. There's movement and stuff happening inside of us, that create things like charge and all this other stuff. And we can measure those things, and we say this pile of thing, when you take into account all the little different things it's doing, this is what its net do is, or this is what its net potential to do is. And so, I don't know if I want to. Look, I'm proposing this. See, simply when you talk about the guy even says in the comments, when you talk about gravity, you end up talking about things like inertia. You have to sort of explain inertia if you're going to be able to explain gravity. And to explain inertia is to understand that when something has velocity, the character of the thing that has velocity is what has changed. It's not traveling some corridor in space. It's not the space around it, as Einstein's theory would essentially. I don't even know if it does really do that, frankly. It would account for acceleration by saying space is bent before you, and that accelerates you. There's a trough you're falling into, and that's why you accelerate, but it doesn't really explain why you keep moving. Even Einstein's description of, as this guy points out, Einstein's description of curved space, when drawn in 2 dimensions, needs gravity to work. So here you have an explanation of gravity, the space goes down. And frankly, that description doesn't work if you don't put it in a gravitational orientation. So there's no capacity to draw it in 3 dimensions. There's no capacity to understand it as a 3-dimensional mechanism, and it certainly is a 3-dimensional mechanism. And obviously we often take the shortcut of a 2-dimensional model just because 3 dimensions just make it that much more complicated, but they're all the same dimensions. There's 3 dimensions: up, down, forward, back, left, right. That's it. That's it. Those circles make the complete circle. You know, those lines, that infrastructure creates everything you need, the components of the universe. Something has to be in one of those fields. Pie hunks, wedges, however you want to describe it. And that's sort of how it can be understood. It's wedges of placement. And as you know, and if your vector is in one of those, then you have a net vector, a net acceleration that is a combination of all 3, where you're moving in all 3 dimensions. So anyway, so yeah, and so inertia is, the idea is that you're just a collection of these little BBs. The universe has them randomized essentially. So there's, say, in the initial condition, or in the planeth condition, they have no net direction. There's just as many going this way as there are this way, as there are that way, as there are that way, as there are that way, as there are this way. So in every dimension they're equal. And it wouldn't really matter if they're unequal in some dimension, because you wouldn't be able to notice it. But the point is the idea is that you start with this inertial frame of equal, and that your condition is in net that you possess a certain amount of these BBs, and if you have a velocity in a direction, it means you have more of these little bits that are moving in that direction than you have moving in the opposite direction. So that's the key to this dimension thing. The dimension always has a forward and a back, a left and a right, which can be looked at as a forward and a back, and an up and a down, which can be looked at as a forward and a backward. You know, they're all inverse directions, vectors, exactly opposite. All right. So you can have an imbalance in up versus down, or left versus right, and that imbalance will be revealed in the sense that what you're made out of will tend to migrate in that direction. The school of fish that is you will have more right fish than left fish, then you're going to go right. It's just going to happen over time. And that's inertia. Inertia is a change in your condition. You've collected fish that are going right. That's what you did. If you go right, well, it's because you collected fish to go right. So we filter out of the mass our identity as a moving thing based on a net disposition of our collected mass, and that's what mass is. So anyway, so from there you can maybe understand what my critique will be of this description. So there's a couple of things he says here. Okay, we understand gravity. We must understand why matter has mass. Physicists have no answer. Well, I think some physicists do, but clearly mass is just is just a collection, an amount of that field of BBs, and you have a collection of them. And important to the idea of mass is the idea that they are in relationships to each other. That means they're trapped, essentially, in a kind of way. So they're more compact, meaning they're closer together, so the BBs are closer together, and that they have a relationship in the sense that they are close enough to each other that they maintain connection to each other. That is, if something happens to one of them, it happens to the other one because the pressure that they impose on each other is changed. So if there's something in front of me and there's a field of straight line pressure on both of us, I won't receive the straight line pressure that's coming from behind the other person, and he won't receive the straight line pressure that's coming from behind me, and there'll be a lack of pressure between us, and that can be understood. If there's no way for the pressure to go around the corner, if it's all has to be straight lines, you can understand that there will be an absence of light, so to speak, a shadow created. I shadow him, he will shadow me. And that relationship now ties us together in the sense that that shadow, if we understand that acceleration is created by imbalances in the field I'm in. So if I'm in a field where there's more pressure behind me and less pressure in front of me, I will tend to be pushed in the direction of the less pressure, and I will gain acceleration. And coincidental to the function of gravity, or incidental, or fundamental to the function of gravity, as I accelerate, I will be in fact absorbing more of those arrows. So if I was, say if I had arrows pointing me forward and I had an absence of arrows coming from behind, I mean I had an excess of them from behind me, I would be gaining as my character changes, as I do something called accelerating in a direction. It just means that now the structure I am in, as I gain something called velocity, will be that I'll have more of those arrows. So as they pass through me, some of them will stick, and of that extra pressure, they will replace some arrow going some other way. So I will release something going some other way at some point in time as I collect something going this way. I'll end up with the same amount of mass. It's just that I'm going to convert. I'm going to exchange a piece of mass that was going that way with a piece of mass going that way. Or more directly, I'll exchange a piece of mass going this way with a piece of mass going that way, to make it all more efficient. So yeah, so your mass is just the fact that you are a collection of this. Like I said, the field is full of this stuff. It's just that you don't recognize it because it's not consolidated, it's not dense. So there's no relationship tying it together. So if you block one, it doesn't change how all the others behave. It just ends up being a straight line vector kind of a thing. It doesn't have any resonance, where we have that resonance. We have that collected effect. You can't tap one piece of us without it bouncing through all the pieces of us, because of that relationship, that pressure relationship that creates tension. See, tension is a key word. It doesn't sound like physics. It sounds more like a mechanical word. You know, mechanics seems a little far from physics, but tension is the key to the transmission. Tension is the key to communicating between one thing and another thing, is to create this tension. But anyway, I don't want to confuse things by adding extra words or extra concepts. Anyway, just to understand the difference between empty space that's actually full of energy and full of matter, I mean full of potential matter, and us is just that consolidation thing. We're just more compactly, we have more BBs per square inch, which, and because they're more BBs per square inch, they communicate with each other kinetically, directly, instantaneously, not at the speed of light. So anyway, no reference to time instantaneous, which contradicts Einstein's speed limit for information. I don't know exactly what he meant by that statement, but he's supporting the idea that there really is instantaneous communication. So the moon and the earth are instantaneously acquiring knowledge of each other's mass and creating the necessary gravity somehow out of that knowledge. And I would argue that no, it's not like that. And people with this electrical theory should kind of understand what that electricity and magnetism have to be induced, that there is a time delay in the creation of magnetic fields and the migration of electricity, and all these things do have they move slower than the speed of light, not faster, if anything. And there's no evidence of anything instantaneously happening. Lightning doesn't instantaneously arrive at Earth. Nothing, there's just no evidence of it. So I don't know why they presuppose the existence of it. Clearly, Einstein doesn't have to worry about time. In some calculations, time is going to be irrelevant, and in some calculations, it's going to be entirely relevant. But when you're doing the big picture in and out thing, you really don't care about time. You're just saying don't be too little. I mean, don't impose too little a time standard. But the equation works fine as long as you're talking about over the period of 5 seconds or something. Then, yeah, the math will always work. Yes, if you abbreviate to some shorter period of time, things might break down, but time isn't critical because it's a net equation for a net process, not for the interior of the process, not for the individual steps of the process. It's an equation describing the outcome of the process. Okay. Big G is the gravitational constant. Has a particular dimension of length, mass, and time. It's just used to, all constants are essentially just limiters, right? They're there to create some kind of backup plan in case your equation reduces to 0, or to keep it within, to create some sort of scale. So you can call it a Kelvin or something, and you couldn't call it a Kelvin if you didn't have a scale. That kind of thing. All right, mass is an energetic variable. Okay, so this is where it's almost correct, but not quite. Mass is an energetic variable, so G cannot be constant or universal. So mass is, when you have a mass, it's full of these little BBs. Yes, the quanta is energetic, but mass is not energetic. So that's where that fails. Is there's no energy in there. No, wrong word to use. There's no expression except in the quanta, in the bits that make up the mass. And the mass doesn't vary. So, I mean, once you've acquired your BBs, your mass will stay the same unless you're acquiring mass, unless you acquire new BBs. So there's no variability in your mass unless the field is imposing a force or something else is happening where you're going to end up converting, where you're going to store more energy. So you could be hit by sunlight, and your chemistry and the physics of your molecular structure could actually do some photosynthesis. It could actually turn some of the sunlight into material mass, in the sense that your electrons could gain energy levels and all that kind of stuff. So you could store some of it like a battery. Not a good battery, but a battery. You'll store some of that and you'll gain some mass. So our mass is only variable in the sense that the field around us has to impose a fluctuation. So we have to be hit by some imbalance in the field. And light is a good example of usually is an imbalance. I mean, when a star shines, there's not a star on the opposite side of the universe shining at exactly the same time. So you can sort of understand that photons of light, which are just the same as these pieces of gravity, they're the same BBs, they're just coming at a frequency, a steady frequency. But they're obviously erraticates, they're obviously imbalances in the field, because they obviously only have, they have a one-directional source. So they're obviously going to be, they're obviously going to create imbalance in the things they interact with, because there's not going to be some obvious constituent photon coming from the opposite direction. So they're kind of an add-on in terms of directionality. They're evidence of a filter. There's been energy from other directions sucked into a star, is now being released in one direction towards you, or something like that. It's not as obvious as that, because the sun basically pulls stuff in and then releases it all in the same direction, equally. But the point is there's directional change that has taken place in that area of space, and that change, the imbalance in that area of space, is now in your area of space, maybe a billion years later. But that imbalance still exists there. That field, the field around that sun, is now minus one BB moving this way, so to speak. But it's also minus a lot of others. So if it's lost just as much in the other directions, then there's no imbalance in that field. But you can get the idea how imbalance can be created by merely reflecting light or doing something else to take the imbalance and send it someplace else. And now there'll be, twice as much going some direction. Not the most articulate way to say it. Let me just finish this lovely cigarette. Yeah, it really, it's been a nice few days. Cigarettes, yeah, it's a holiday pleasure. That's what we'll call it. It's so nice. So yeah, I'll play some of this. I mean, I stopped at this point. I'll play a little bit, and then I'll see whether I need to stop and come back and do whatever. But this, yeah, I say my argument here with these people is that it's just, unfortunately, they're betting on the wrong horse. Electricity isn't even really a thing. I mean, electricity is a description of the movement of quanta through usually material objects. So they're being transferred by electrons or something else. They're migrating through a pathway created for them by the structure of matter. And they're just a kind of gravity moving through, being channeled through a mechanism. And the polarization is the same as the polarization of light, except this expression of polarization in gravity creates this phenomenon of electricity and magnetism. So I don't know. I probably won't get into that, but it's that simple. But so they're betting on the wrong force. The fundamental force isn't electricity. The fundamental force is gravity, or this idea of this field of bits. And so you have to go there first. I mean, the gravity is the first force in the sense that it's essentially the only force. It is the movement of quanta that is everything. And all you're talking about is imbalances in the distribution of quanta moving in a particular direction. So it's just, again, just collecting out of a field of randomness, out of a field of, I mean, I hate to use that word, but I just mean to imply a balanced field. And then through, because there's something in, left over, some residue that stuff can hit after a big bang or something. There's a collection, a clogging, and once you clog in one area, the clog will tend to expand, and that will steal, it will absorb these BBs out of the field. So it says, I thought of an argument for inertia. It's like with your velocity changes not only when some other force acts against you, like you could just say gravity, the little bits that are coming down because you're getting more of them because the sun is blocking a bunch, but more importantly the earth below you is blocking a bunch of the arrows coming up, and so you're getting a bunch more from down, so you're getting a higher density of down arrows. And if you have velocity up, you're fighting that force. But in other examples, like a plane flying through an atmosphere, the force that's blocking it or taking away or depriving it of velocity, that will cause it to lose velocity in a lateral direction and gain velocity going down because of gravity. But the one that the friction, that's the one stopping it from moving, the force isn't because another force is coming at you. The force is that you're giving away your velocity as you hit these little things in front of you, as you hit these other bits of matter. you're giving them acceleration. And for them to accelerate, you have to give them extra arrows. And so you're giving away your velocity to the other matter. And so it's not like there's some opposing force. It's that you've given away your identity, your velocity. And that's how you stop. That's what stops you, is that you just keep giving away your arrows going in the direction you're going. So, you know, if you're going this way and you hit stuff that you make it go that way, you've given away your arrows, and now you have less of those velocity arrows. You have less imbalance. It's that simple. It really is. I mean, and when you give them away, you're essentially exchanging. So when you give them a forward arrow, they'll likely give you the Newtonian inverse reaction backward arrow. And so your balance, you'll just keep losing. If they were colored jelly beans, you know, and red meant forward and blue meant backward, you're just basically giving them your reds and they're giving you blues, and that's why you lose inertia and velocity. Alright, I'll play some of this.
That means that big G, which we measure on Earth, is neither universal nor a constant, and in fact it's the worst defined constant in physics. Every time it's measured it's different, and even using the same equipment it varies. So what I would suggest is there is more complexity in the effects attributed to gravity. I say attributed because in some cases we're looking at actual electromagnetic force.
Alright, so these are kind of these, they always do this with dinosaurs, you know, they say it's too big, its neck is too long, it would break. It was, you know, I mean, it's kind of obvious though that it did it. So there's probably a mechanism or a reason why it did it. And I thought the explanation that these were more grazing animals than the tall tree kind of thing sort of made some sense. So they're not really made like giraffes. I mean, they're made a little bit like they could tilt, you know, their whole body. But I think their necks were pretty rigid, and that, you know, they did just go side to side a lot, and so it wasn't a flexible neck, you know, like we have. So you know, it could take a lot more weight. But they obviously did have little tiny heads, you know, so they weren't carrying much weight on the end of that long. But anyway, in this whole thing that pterodactyls couldn't fly because of blah blah blah, look, they did. So it's just no point in, you know, no point in wasting time saying they didn't. And who knows how well they flew, right? Flying squirrels fly, and you'd say, shit, okay, if somebody thought they were flapping their wings and flying, well, yeah, that's stupid, because they're gliding. So pterodactyls were probably just doing a lot of, you know, that thermal thing. They probably hit the thermals, and they were doing a lot of hang gliding. They probably weren't very good flyers. All right, but anyway. There is more complexity in the effects attributed to gravity than any equation yet devised can explain. I don't know exactly what that means, but you know, sorry, I don't know what some of these little blurbs aren't very useful because they're not really straightforward. I should get my big G straight. Like I said, I thought big G was the gravitational constant. So, but you know, whatever.
Forces, and I'll talk about that. That's mistaken for gravity.
You know, I don't think, like I said, the constant to me is sort of irrelevant to the I think it was invented, like I said, pretty much for the purpose of keeping the universe static, and you know that it has lots of uses in the math, but I don't think it has any uses in theoretical physics. I don't think theoretically, to understand what's happening in the universe, you need any constants at all, technically. What you're looking for is the mechanism, the thing that's doing something, not the thing that's not doing something. And a constant is kind of implying a nothing.
It has more complexity than any equation yet devised can explain. It depends on the context whether it's actually valid or not. It's not universal.
Yes.
We repeated the mistake of Earth centrism. In other words, we measure G on Earth and then apply it throughout the universe. What gave us the right to do that?
Okay, so that's a kind of a bold claim, right? We repeat the mistake of Earth centrism, and we have selective blindness towards conflating evidence. But this whole idea that, look, I'm certainly arguing that it's possible at the ends of the universe gravity dissipates and disappears and everything just falls apart. But we kind of know just from function that, you know, that the fundamental equation, this inverse square rule, is sound. And we certainly can understand that the elements have a mass, and that mass has a shadowing power, and all those rules are the same. And so I don't know what evidence they're using to pick on the idea that, you know, the function of gravity in some other solar system in this galaxy is different than the function of gravity in this solar system, or that our galaxy is functioning under some different rules of gravity than a galaxy 5 billion light years away. I just don't, you know, where do you have any evidence of that? They're shaped similarly, they move similarly. The evidence is that gravity's basically pretty consistent, and we certainly, you know, and where it starts to lose meaning is when you start looking way back in time by looking at things very far away. See, we can't see things very far away today. Like the stuff that's very far away today, you know, we have no hope of seeing. All right, I mean, it's billions of light years away, and it's making light today. You get it? And the light's not going to get here for 15 billion, 20 billion years. We're not going to see anything that's out there now. We're just seeing what was there at some time that we consider to be near the Big Bang. But I'm saying I don't even think that's what it is. I mean, if it's 15 billion years out there and we're seeing it, it took a long time for it to get there, because it didn't move faster than the speed of light to get there. So if we say the universe is 15 billion years old and we've seen the light from something 15 billion years old, then you can say right from that, if it doesn't look like a Big Bang, if it doesn't look like it's in a place all coming from the same place, then clearly it's way out there when we're seeing it, which means the universe has got to be much older than where we're seeing the first light from. But that, you know, it's just deduction.
So we have selective blindness towards conflicting evidence, and we invent dark matter and dark energy, all this stuff.
Well, again, I would agree that I think those contrivances, and that's what they are, they're pretty much just contrivances. They just invented them for the purpose of making things to add up, to force mass where they can't find mass, to explain phenomenon that they can't explain by the proven theories they say they have. They say they have these proven, reliable, it always comes out, it always works out. Well, it always works out because you always come up with something like dark matter or dark energy or some other bullshit to make it work. Because obviously it doesn't work without it. You know, I mean, the most proven theory in the history of mankind. Yeah, because we put Tabasco sauce on it.
And for example, these pictures that I've got here, and as Anna said in her talk, we ignore the fossil record of impossibly huge creatures. The ultrasaur, in today's terms, would have weighed 180 tons. And the maximum force exerted by any muscle is independent of body size and is the same for the mouse as the elephant. In the antediluvian
well, I don't think any of that's true. There's clearly, I don't know what, I guess I'm not understanding what he just tried to imply, but there's absolutely no, the mouse and the elephant are living in very different stress points. Elephants are kind of pushing the theoretical envelope. They're really vulnerable because there's a hell of a lot of stress on their bones. They're pushing it, and mice are the other way around.
Well, 350-pound flying creatures soared in skies which no longer permit flying creatures above 30 pounds or so. And the ultrasaur's neck in today's gravity would have caused a 430,000 foot-pound torque where it attached to the body. Even a steel girder of the same mass as that neck would have sagged under that weight.
Yeah, I'm just saying that, biology finds a way, quoting the movie, right? And so sagging is the least of its concern, right? A little bit of a sag in my neck wouldn't bother me too much. So maybe this image just isn't correct. Maybe his neck did sag and then it curled up here at the end. I mean, the fact that you want to make it look, they want to make it look strong. Well, they can go ahead and do that. But maybe it wasn't. And again, once you've established this capacity of rigidity in this, like I said, all you really need is a tipping point, and you just tip the organism this way. And so if you don't use the neck as the lever, you don't have to have any muscle control over the neck, and you just use the body, you can certainly lever that thing further out. So I mean, if you're going to assume flexibility, then you have a problem. But if you assume rigidity, then the math gets better.
Also, we know observationally that spacecraft show anomalies in Earth flybys, and comets exhibit what's called non-gravitational forces. That's what makes them difficult to predict their returns.
I don't know anything about that. Non-gravitational forces. Certainly they have explosive problems. I mean, comets are volatile, so obviously if you take a comet and you run it near the sun, it's not just gravity that's going to be relevant anymore, because the comet itself on one side is going to be emitting a huge amount of gas, and on the other side it's going to be just sitting there saying, I'm fine. And that's certainly going to have a non-gravitational effect. I mean, strictly speaking, traditional gravity.
And people who have measured gravity, or the change in gravity as you go down deep mine shafts and so on, actually said it looks like there's a fifth force. It's not changing the way we expect from Newton's law. And people who have measured gravity going up towers have said maybe there's a sixth force, because that doesn't conform to Newton's law either.
Well, maybe. This is a lot of maybe stuff here. So I don't know what you're measuring. I mean, the trick with going down tunnels is that you're taking your atmosphere with you, and now you've got a buoyancy issue, and so that kind of you have to recognize that we're floating in an atmosphere, and just as it changes Newton's strict gravity, I mean, just as quite obviously, right, the Leaning Tower of Pisa, I throw a bowling ball and a feather off the Leaning Tower, the bowling ball gets to the ground real quick, and the feather could take days. It could end up in Mongolia. So yeah, it's going to be affected by the atmosphere it's in. So I'm just saying, I think if you have a mine shaft that's a vacuum, you take the atmosphere out of it, and the buoyancy issues created by the atmosphere, and the same with the tower, you create the same air pressure at the top of the tower that you have on the ground. I don't think you'll find any fluctuations in gravity. I mean, anything outside of Newton's predictions of inverse square.
It was pointed out to me a few months ago that if you calculate using Newton's law the force of the sun on the moon and the force of the earth on the moon, when the moon is between the earth and the sun at new moon, the sun is pulling on the moon twice as strongly as the earth. And the question is, well, how do we have the moon? That's a good question.
Well, because pull is the tricky word you just used, right? I mean, it doesn't pull, it's a pushing force. So you have to think of it as a pressure force. So when the earth is behind the moon's going to be gravitationally locked to the earth. All right, so then even though the earth is blocking force as far as the moon is concerned in just that direction. So there's not some sort of additive effect. The sun's gravity is consistent. The sun makes its gravity. It blocks. It creates a shadow. Everything else creates another shadow. And you can't just add the shadows up, because there are shadows in different directions. The gravity imposed on the moon from the earth is an opposite gravity to the direction of the gravity that's being imposed by the sun. So they don't add up. And that's why the moon's vexed or whatever.
None of these questions are answered by Newton's simple equation.
Well, they would be if you counterbalance the question. If you just merely say in Newton's equation, the premise is, okay, that the alignments are constructive, not destructive. So as long as you say that the alignments are, you know, all going in one direction, there's nothing wrong with Newton's adding the masses. But you can't add the masses if the masses are, if 3 is in between 2 and 1, it's not going to work. It has to be 1, 2, 3. So that's the only rule. The rule is you can't use gravities that have directional vectors in conflict. All the gravity vectors have to be in the same direction with the two things on the two sides, essentially. The thing being affected by gravity and the thing affecting the gravity, those two things have to have the same gravitational vectors. The two things on the two sides of the equation have to have the same directional vector. I mean exactly complementary. One has to have that direction, one has to have the opposite direction. They have to be exclusive and in opposite directions. Otherwise the equation's fine.
Of course, if big G is universal, if we use G measured on Earth's surface, the comet 67P looks like solid rock, while its density appears to be that of highly porous dust and ice. And I have repeatedly in the Space News on the Thunderbolts website pointed this out. The planet Saturn appears...
Well, the appearance is something. I mean, what it looks like on the outside don't have much to do with what it is on the inside. So, frankly, you know, you can add up to having a mass because your interior is uranium or something. You know, your exterior could be helium and your interior is uranium. Then you could look like you weigh as much as a brick. When, you know, on the outside you look like you're peanut butter or marshmallow. But anyway, I'll come back to this. Right? I'll play one more little section.
Is to have a lower density than water. It could float in water according to using big G as we measure it on Earth.
Okay, I don't know exactly what that is, so this is comet, let's see. The planet Saturn appears to have a lower density than water. Again, this appearance, you have to go by the net value of the planet, so there's just no point in talking about what it looks like on the exterior, because the thing that's going to matter is what it is in net. And so what is when you add them all up and you divide by the surface, I mean the collected area, that's all that matters. The net, the average mass, not any particular area of mass. So and the sun is calculated to be mostly hydrogen right down to the very core. Why not? I'll see what he says about that.
And the composition of the sun is calculated to be mostly hydrogen right down to the very core. Now what body the size of the sun would have hydrogen gas in its core?
Well, you say hydrogen gas, so right there, trouble. It's under sufficient pressure to be probably liquid or some other form, okay, of hydrogen. It's not gaseous hydrogen as you know it here. It's so regardless of the idea that we associate freezing things, you know, gases having to be very cold to be liquid, what all they really have to be is under pressure. So the fact that this is a very dense gravitational body means that the stuff on this, the stuff is being accelerated constantly, and besides that acceleration taking place, it's stirring it, the weight, you know, each bit of this stuff can't fulfill its gravitational destiny. All this stuff is suppressed from moving where it wants to move. So all this stuff that's not the center, anything away from the center is going to feel more gravity as you go further out, and the most gravity is right here on the exterior. So that's the irony of gravity, or the trick of it, is that the highest gravity is on the very outside edge here of the density. So where the density is the highest, you know, there's a line somewhere, right here near the surface, that's the highest gravity this body creates. And so you can just imagine the highest gravity has the highest pressure, because the stuff has acceleration that it can't realize. We're pushing down on the interior of the earth, right? You're sitting on your chair. No, you're sitting on the center of the earth. You're squashing everything below you. The chair goes through the floor goes into the ground goes into the substrate. You're pushing everything going towards the center of the earth. You're pushing on it. So the entire mass of the earth essentially is pushing on that stuff in the very center. So there's no, in spite of the fact that there's no gravity in the center of the earth, there's a ton of chemical pressure. Okay, so we're back to this buoyancy idea. The matter itself is pushing. And it's just the fact that matter has a tendency to create shields, skins, that they don't just push together. You just can't push peanut butter into a steel bar. You can't just say, oh, here's some peanut butter, I'll just push it into the steel. You can't, because the steel has a surface. It has a resistance to acquiring less or more density. It's locked hard in its relationships. The little BBs are relating to each other strongly, and you just can't push new BBs in. You have to push them in a particular kind of way to get them in. And so it's that pressure that probably has the center of the sun quite dense with hydrogen, liquid hydrogen, solid hydrogen. What the hell do I know? Probably liquid, though. Certainly not wide-spaced gas molecules. They're highly compressed gas molecules. And they might act like a liquid, but they're probably technically a gas, but they're being forced to behave like a liquid. It's like the opposite of a super-cooled superconductor. It's like a superheated plasma. That's probably a good point. Anyway, we'll pass. we'll leave on that point, and I'll play some and listen and take some notes maybe, and see what else we need to cover. Well, that's the only way to do this, right? I mean, I can't play an hour-long videos on it with a 4-hour response. So anyway, I'll be back. I have returned. So I watched, I think all of it. So anyway, I'm going to end up going back and playing it. So I might make a second video. There's a lot of points to be raised, and these people. It's just kind of funny how they're so close to getting it right, and it's just this. Once you dismiss what's an idea or a concept, you don't really have an analogy for it, but there's probably an analogy. You get an idea of what something is, and then you just can't get free of that idea. You dismiss something, and it's just dismissed for all varieties for all time, and you can't even say the word anymore. So I know there's lots of things like that I could use as example, but I don't have one off the top of my head. But anyway, it doesn't really matter. It's not really the psychology of it that I want to get to, but it's just so the point is, it's just so they just got stuck on this I love electricity thing and just didn't realize that it's just the wrong starting point. So the key point I would argue is that this whole thing they're saying is this electric universe. They're talking as if they're explaining something, but they're leaving a huge hole in the sense they're just saying there's this attractive force, this charge, and they don't account for how it functions. They just say this charged particle moves towards this charged particle. Period. They're attracted. No explanation. No statement about mechanism. Just is. Where if they would have taken stuff that was started 300 years ago, let's say gravity, and just made that a kinetic force rather than a force made of. So the funny thing is, they think of it like it's they think of particle. What do you call it? Particles in a physical in our physical world rather than in a nuclear world where it would be kinetic, and they don't really understand that heat isn't a byproduct. It's made of this very substance. But anyway, you know, I mean, even the sage used the word ultra mundane particles as a way of kind of, stating these are small. You can't, they're so invisible. But that's only from perception, and in mass, they're everything. So the other important thing I wanted to say was getting back to, again, how it's almost, we're looking at it backwards. The place we see energy is kind of where there isn't energy, ironically. I mean, the energy's in the universe. The energy is full of these little bits bouncing around, and as long as that energy is balanced, you don't see it. There's no effect. And there's only effect when you break it, when somehow you shadow it, you have an absence of it. Then it reveals itself. So it's like the void is where the action is, because the void has to be filled. So if you push the energy out of the way, if you push the field away, you somehow remove it, imbalance it, that's when you'll see it. And what you're really seeing, though, isn't really an imbalance in the field. You're just seeing an imbalance in the makeup of the field, in the sense that whether the key will be polarization, so whether it's this way or this way, and whether it comes at a frequency. And these are the key things to what we see as energy. It's just a form of the migration, the movement of this field. But it's all something real has to move for something to move. Something real moves, and it moves into something else and causes it to move. There's no invisible force beyond the initial force, which is just the idea of this little bit, photons, graviton, quanton, moving at the speed of light in a straight line. You start with that, and you just make a whole lot of it, and you have a universe. Okay. So, we'll do this little Faraday part. The long and constant persuasion that all the forces of nature are mutually dependent, having one common origin rather than being different manifestations of one fundamental power, has often made me think on the possibility of establishing by experiment a connection between gravity and electricity. No term could exaggerate the value of the relation they would establish. Well, obviously, the value is diminished. I think, even though Einstein's statement of E equals mc squared doesn't unify anything necessarily, it pretty much does what they didn't say at this time. So what was missing here was an understanding that matter is effectively, and I would say quite literally, energy. And it's just trapped energy. It's a battery. Matter is a place where form of energy is all it's doing. It's just holding a form of energy. Close enough.
Stations of one fundamental power, once again the electric universe idea, has often made me think on the possibility of establishing by experiment a connection between gravity and electricity. And he went on to say, no terms could exaggerate the value of the relation they would establish precisely. Now, if people had followed Faraday's intuition, we would be several centuries advanced, I would say.
Yeah, I really don't think so, just because most of I don't think theoretical physics does much to advance anything. I think it's real practical, hands-on stuff, and theory doesn't lead to anything. Realistically, you get an idea that something's possible, and then you play with it, and you make the possibility into a reality, and I think that's how most of it happens. So I don't think theoretical diagrams are necessary. Anyway, but besides that, whether we'd be advanced or not, the point is I would say the same thing to this guy, to Wallace. That, if you paid more attention to Lesage gravity, he's going to mention it in this video, and he just dismisses it with the same dismissal that people he criticizes, like Richard Feynman or somebody else, he dismisses it with the same casuality that, as if there's nothing to this idea. And then he cites another guy citing Lesage gravity, which is ironic, as being something that's more viable and more consistent with cosmological observations. So there's a duplicity there in the sense that he's dismissing something, he's saying this guy's got something right when he's arguing in defense of it. So I mean, that doesn't even make any sense. But anyway, but I mean, you had the pieces, and you wasted them because it's this because stuff. I mean, really, it shouldn't have taken me. I shouldn't be the one who did this. It should be somebody better than me should have figured this out. It just should be.
In our science. But of course, this poses the key question. The electric force is both attractive between opposite charges and...
Okay, but this poses the key question. Why is gravity only attractive? So again, it's not attractive. It's a push. So it is all push. And obviously push looks like attraction when you're inside the push, when you're on the wrong side of the shadow, when you're on the wrong side of the reduced pressure.
And repulsive between similar charges. But gravity seems to only attract. Why is that so?
Right, but it's not really what it does. I mean, repulsion is just actually the reversal of the pressure. So the argument's pretty simple in the sense that, there's no point in me going through the whole thing. But if I convert everything to something you don't like to eat, or I convert it all into stuff you do like to eat, it can have the same mass of food, same amount of food, but the amount of food you're going to eat is going to be very different depending on what form the food is in. So if all I throw at you is food you can't eat, then any smell from the other direction is going to be powerful, where, the nature of repulsion. And the inverse would be true. So it just has to do with the sensitivity, which one affects you more. And that would be the illusion of repulsion, is really just the absence of a pressure again, because you've converted the pressure into something you find uninteresting. Your matter finds uninteresting.
And here's a character who was around at the time of Einstein. Sir Oliver Lodge was a British physicist and writer best known for his contributions to the development of wireless telegraphy. He perfected a radio wave detector and the heart of the early radio telegraph receiver. He was the first person to transmit a radio signal 1 year before Marconi did, and received international recognition for his work.
It is kind of curious, just because this guy does do some name dropping throughout this video, but he doesn't mention Tesla, which is kind of interesting. I don't know enough about. This smells like Tesla, and it just seems strange that Tesla is not mentioned in here.
Lodge is also remembered for his work on the ether, which had been proposed as the wave-bearing medium filling space.
There you go, wave-bearing medium. So this is where they make their mistake, is they, just like Einstein's empty space, creating a medium without defining what this medium is made out of. And again, how this medium, you can't, well, they try to, but you can't account for the energy in the universe by just looking at the things that possess it, the matter, because the motion isn't being controlled just by that. The gravity is sort of free. You don't burn anything to create gravity. So you can't account for the motion in the universe if you just go with the matter and the energy in the matter, because there's no loss of energy in the acceleration being created by gravitational attraction. Neither body loses any energy in that process. So you have movement without any impetus, any force. And so if you would say ether and understand the ether to be energetic ether, then you have something. So again, it's just a simple, a simple change of the description. Go from an ether to an energetic ether that's capable of carrying, that you can you can sail on. And I don't want, I mean, it gets a little complicated, the kinetics, but the idea is that it's not like light isn't sailing on the ether. Light is made of the same stuff as the ether, and it travels without any obstacle through it, because it merely exchanges direction through it, and so it retains its frequency, it retains its period through it, even though it's a moving force. Even though everything in front of it's moving, the frequency keeps going. The actual thing, the actual BBs are what changes, but what doesn't change is the direction of the initial BB.
And of course, which the electric universe relies upon.
I guess this is the thing I wanted to, direction never changes. You can't get rid of it. You can't destroy the direction that exists in the vectors of the BBs. They can just exchange it, and by exchanging it, they can filter pockets of it, and that's it. They can filter out of it more right than left, but they can't change the fact of where stuff is going. They're just changing what stuff is going left and what stuff is going right. Who possesses what's going right? You're always traveling on the ether, so to speak. You're traveling on the force that exists. You're not making force. You're just traveling on force. And force can be it's almost like you're changing how bound you are to it. You don't change the force, you just change what rail you're connected to. It's like streetcars with a bunch of cables running in different directions. You bite onto a cable, and then you bite onto a different cable, and you bite onto a different cable, and depending on what cable you're bitten onto, that's which way you're going. Probably the better analogy. The school of fish works too, but I won't do that in this video.
Scientific work included investigations on lightning, the source of the electromotive force in the voltaic cell or battery, electrolysis, the application of electricity to the dispersal of fog and smoke. He also invented electric spark ignition for the internal combustion engine.
Well, I mean, that's sort of a... well, I'm just saying, it's hard to call that one an invention. I mean, once you create spark and you understand it, hey, that can start a fire. The plug is like the nothing part.
Man, rather like your Faraday, he's prepared to experiment and try things. He was critical of the new theories of relativity proposed by Einstein. I would suggest that if education was done properly, his arguments against Einstein would be placed against Einstein's arguments, and students allowed to judge for themselves.
Well, I'll keep that in mind. If I can go find some Hodge writing and see what exactly those arguments are. I mean, I guess you should have, if you're going to post little comments and stuff, maybe you should have a couple of his anti-Einstein quotes there to be viewed. Maybe.
Referring to Isaac Newton, he wrote, "What is really wanted for a truly natural philosophy is a supplement to Newtonian mechanics, expressed in terms of the medium which he suspected and sought after but could not attain, and introducing the additional facts, chiefly electrical."
Okay, well, So that's their add-on, is the chiefly electrical. I mean, the fact that Newton did consider Lesage gravity, he was a fan of it for a while, and then had a fight with the guy who was in favor of it. Who knows what transpired, and who knows, it's a soap opera of some kind. But anyway, but again, the reason why they couldn't make it work is because they didn't apply it in the world it exists in, which is a world where there is no friction, and there's no falling apart, there's no breaking into smaller bits, there's nothing that can happen. You can't possibly make energy. It's just that two things, one going this way and one going that way, that they interact, and the outcome is something's going this way and something's going that way, but it's not the same thing going that way. It's just a change in direction. The thing changes direction, but the outcome is exactly the same as if they'd never hit each other, which is really interesting.
Especially the fact that variable inertia discovered since his time. That was in Nature, Treb 7.
Well, the fact of variable inertia. So again, there's no variable inertia. There's no variable velocity. You either lose it or something imposes some other velocity on you. So you're either accelerated in an opposite direction or you give away your velocity to something else. But there's no variability. And there's certainly no variability in the quanta that make up the ether.
In 1921. Lodge seemed to be fully aware that Newton's mechanics needed to take into account electrical effects on the masses involved.
Okay, Lodge seemed to fully be aware that Newton's mechanics needed to take into account the electrical effects of the masses of the particles. So again, the electrical effects is it's just saying electrical is a kind of gravitational. So I mean, to tell Newton that he had to consider gravitational effects on masses, I think is incorrect.
Is a pivotal idea for gravity.
Well, it is gravity. It's just channeled gravity. Again, it's the same mechanism. Photons are gravity. Electrons, everything's made out of the same kinetic element.
Understanding gravity is essential to be able to express mass in terms of weight in kilograms.
Well, I think it's, again, see these people, they really don't get the E equals mc squared things in any kind of realistic sense, this electrical thing, because electric is just carried by these elemental atomic particles. So mass gives you a capacity to carry, to create pathways, or to block, as pointed out in a sense. But again, blocking isn't really blocking, so let me not create any confusion. When I say two bodies block gravity, they don't really block it, they absorb it in creating acceleration. They're absorbing the direction, and that direction will eventually leave in some other direction, but it will leave. It's never created or destroyed as stated. So all it can be is delayed, it can be suppressed in its migration.